Hi, everybody. Thanks for joining in on time. We're going to get started right away at 5 today. We're really excited to bring to you Danny Hillis. So Danny Hillis is a visiting professor at the Media Lab. He was also my PhD committee member, and throughout a really interesting life has founded or co-founded a number of fascinating technical organizations: Applied Minds, Applied Inventions, Thinking Machine, Parallel Computing, which some of you may be familiar with, should be familiar with. And today he's going to talk to us a little bit about his passion for space exploration and this famous rocket lecture that he gives every year for us. And then if you're lucky, maybe also a little bit about the 10,000-year clock. And what I'd love for everybody to listen to and think about as he's sharing these themes is the passion that Danny has for space exploration, and then also thinking about designing robust engineering for long time horizon. Is really applicable for us, even though we might not be doing this for our individual prototypes, but it's important for people who are thinking about space engineering and space design to keep these themes in mind. So thank you, Danny. And with that, I will pass the microphone to you.
Great. Thank you, Ariel. Yes, the theme today will be about long-term. And it's a natural thing if you think about space exploration. And so the first part of the lecture will be about why that's true, why long-term thinking is a sort of necessity if you're serious about space exploration. And then the second part will be about another long-term project I'm doing where I'm embodying some long-term thinking. So let's see if we can get the logistics to work. This is the first part, which is a slightly discouraging talk if you thought space travel was easy. But it's true. So embrace the truth. And one of the basic truths about rockets is that it requires a certain amount of speed to get from one place to another, even in the solar system, and of course out of the solar system. So that's the delta V. So it's basically your change in velocity. And in effect, to get to a different orbit, or if you're going to a different planet, you're going to a different orbit than Earth's orbit, you have to catch up with the speed of that planet. You have to be going at a certain speed in order to get out that far. And to get out of the Earth's gravity well, you have to, in effect, you have to get up the speed to go into orbit. You have to get up escape velocity. So there are distances between places that you might want to go in space, which are very much set by this delta V, the change in velocity that you have to get from one place to another. And so this is a map of the solar system, which I grabbed off a website. You can find different ones showing you, from various places, this being our starting point, Earth. Let's see, I don't see a mouse.
Yeah, I'm not seeing a mouse either. I saw it before when we tested it.
Well, let me see if I can. Oh, well, I think, but the little blue dot over there is Earth. And you can see that, you can get to the moon is pretty close by. Things like, L3 are pretty close by. But to get out to the other planets, there's quite a distance of delta V. And there's just a certain amount of changes in velocity that you just have to do. There's no shortcuts. Now, shortcuts become important if you worry about the time it takes you to get there, of how long a trip you take. But you have to have a certain amount of delta V, for instance, to get to Mars, even if whether it's close or far. And so that's just a given of rockets. So the other given of rockets is that they have to carry their own fuel. And in fact, an awful lot of their power goes to carrying their own fuel. So that's where you get the rocket equation, which basically says that rockets become exponentially less efficient depending on the amount of delta V that you get out of them, because they have to accelerate all the fuel they're going to use right at the beginning. And then just burn off of the fuel. So there's a couple of ways of doing it, but it's all scales with the exit velocity of the rocket exhaust. So if you solve the rocket equation and sort of put it in terms of payload, you can see that the amount of payload you get decreases exponentially with the exit velocity decreasing. It's the ratio of the exit velocity to the delta V is in that exponential. So that means that things are, in the nature of the exponential, things are either easy or hard, depending on whether that ratio is positive or negative. I mean, whether the exit velocity is greater than the delta V that you want to get to. So rockets are very, very good for reaching relatively small velocities, which is why bottle rockets work so easily and so well. But they're pretty bad at going long distances. So another way of looking at it, if you actually graph this, is you say that the exit velocity of the rocket, you can get an idea of what kinds of mass ratios are recent. So you can sort of see that what I mean by the easy or hard, that the the easy zone is where it's going up to the left, the hard zone is where it's going off to the right, and you get very small mass ratios. So it turns out that a very good way of measuring for exit velocities is to measure them as a ratio of Earth's gravity. Now that sounds funny, that sort of gets an odd unit. It turns out it gets a unit in seconds. And a way of thinking about that is if a rocket just burned at a rate that was possible for it to float in air, how many seconds would it burn before it ran out of fuel? So if it has very fast fuel, it can stay there for a very long time. If it has very slow fuel, it'll burn out of its fuel very quickly. If it has this, and drop. So that's a good sort of way of visualizing is how long can a rocket just float in the air? And that lets you measure the quality of different kinds of fuel and different kinds of rocket engines. So that's a really useful, that sort of what's called specific impulse is a really useful metric of how good your rocket fuel is, how good your rocket engine is here. And an engine can only get the very best that's possible for the fuel, and it sort of depends on how much energy is in the fuel. So a lot of progress for rockets for a while was getting fuel with better specific impulses. So just to give you an idea, the bottle rocket I talked about has a specific impulse of actually only 0.3. So that's the gunpowder rocket. Actually, I'm sorry, the gunpowder rocket has 80. The bottle rocket that has running compressed air of the kind you probably pumped up with a bicycle pump, that has a specific impulse of less than 1. So it doesn't go very far because the fuel doesn't come out very fast. But a gunpowder rocket has a specific impulse of about 80, so that means in principle, if you built a perfect gunpowder powered rocket, it could sit there for about a minute just burning its own fuel. It could float in the air for about a minute. And what's amazing is how good jet fuel is. So if you built a great fighter plane that could ride on the edge, it could actually float in air for about an hour just on its own fuel. But it has an advantage over a rocket, which is that it's getting its oxygen from the atmosphere, and it's also getting some of the air that it's expanding and throwing backwards from the atmosphere. And so it's really almost impossible to get a rocket by normal chemical technology to perform any place in the vicinity of jet fuel. And in fact, the very best solid rockets that have ever been built, like the boosters for the Apollo system, have an impulse of just a few minutes, a specific impulse of just a few minutes. And indeed, they burn for just a few minutes before they drop off. If you remember, what the space shuttle looked like, the solid rockets burned off right at the beginning and then dropped off. The best sort of normal fuel that we have is a hydrogen oxygen rocket. And that is in fact used for a lot of long distance space missions because of its high ISP. The best anybody has ever even theoretically come up with is this very elaborate trichemical thing that involves fluorine, and it's only slightly better than that. And since those chemicals are incredibly toxic and corrosive and hard to handle, that's really not used. It doesn't gain you that much. There are some people who, suggest, getting up in the 500 range or something like that, but we're talking about very small improvements at this point. That you're sort of running out of what chemical energy can do. Now, there's potentially a couple of other technologies that could do much better, but they tend to be very low thrust as we have them today. One of them is an ion engine, where you're basically using an electronic particle accelerator, and you're taking, say, an ion of mercury or something like that, and accelerating it through an electric field. And that, because you can accelerate up to some fair percentage of the speed of light, can have a much higher ISP. And so, in fact, engines like that are used for instance, positioning satellites and tweaking them, not orbit change maneuvers, but tweaking the position of satellites, because they use very little fuel to get a lot of impulse. And those kinds of operations require very, very tiny forces over long periods of time. So I know there's at least one MIT spin-out that's in the space ion engine business. If anybody's interested, I'm happy to introduce you to them, that are commercially making ion engines for extremely low thrusts for positioning, for repositioning drifting satellites. There's also been another thing which on paper is even better, and it sounds very silly, but it's probably one of the more practical ideas if you really want to move around the solar system, which is that during the 60s, back in the days when they were testing atomic bombs in the atmosphere and everything, Freeman Dyson and a bunch of people from General Atomics actually worked out a scheme where you could build a very, very large spaceship. And I'm talking about something the size of a battleship, giant building size thing with a big, thick steel plate underneath it. And you would actually propel it up by dropping an atomic bomb out the bottom of it. And the bomb would explode, and there would be springs between the plate and the rocket. I mean, it sounds like a crazy contraption. And that would push up the battleship, and then you would drop another atomic bomb. And so you would put a string of atomic bombs as you went through the atmosphere, and then as you kept on going, you would accelerate with atomic bombs. So of course, such a thing was never built, but it was actually very carefully calculated out about how it would work. There's a book about it called the Orion Project, if anybody's interested. And it does indeed work in principle. So if you really needed to, get to Ganymede with your luggage, right now, this is kind of one of the only ways that is possibly known how to do it. It's either that, or you have to make yourself very small and not carry much luggage. in which case you could do it with a gigantic chemical rocket. But notice, but by the way, we've never gotten to Ganymede. We've flown by Ganymede. So the delta V to actually stop someplace and is actually higher than the delta V to fly by it. So that's a crazy idea. And then there's another idea, which I think is maybe more potentially the right thing of the long run, which is the notion is leave your fuel on the ground and only take your reaction mass with you. And so the way that you get the energy there is by something like a microwave beam or a laser. And so if you could shine a laser at your flying rocket, it can somehow capture that energy and then use that to heat the fuel, then it can heat the fuel to extremely hot. It wouldn't be limited by the chemical properties of the fuel. And it could potentially shoot out at a very high rate. And so there, I think, some plausible ideas about how to do that. For instance, having the fuel be just a plate of plastic on the back of the rocket, you shoot a laser pulse at it and it ablates, and that's your fuel. Or the more sophisticated ones, you shoot 2 laser pulses. You shoot one, it ablates, it makes a little cloud of fuel behind plasma behind it, and then you shoot another one into the plasma, which totally absorbs the laser power and heats it up even more. And so if I were to bet how we're going to get to the stars, which I think we will eventually, I bet it's probably going to be either atomics or some kind of laser system that stays behind. But we'll see. Well, actually, maybe we won't see, but somebody will see. So if you kind of look at what's achievable on those curves, what I've got there is I've got two, and those were 2 curves that I showed there is the delta V required to get to Mars and the delta V required to get to Earth. Same lines that were on it. I mean, I'm sorry, to get to Earth orbit. So what you can see from this graph is that, remember, chemical fuels were kind of in the 250-ish range for solid rockets. This says it ought to be pretty easy, at least if you could build things perfectly, to get to Earth's orbit with a single stage solid rocket. And in fact, that's quite in the doable range. And in fact, if we have fuels that are in the 450 ISP range, getting to Earth's orbit looks really easy on that graph, at least. But remember, the graph doesn't count it. The graph is the limit of the best you can do. But certainly it seems like the chemical fuels are easily what you need to get to Earth's orbit. If you look at Mars, it's a little iffier. You need to really use the very best chemical fuels, like a hydrogen rocket. And you need to actually, you're not in the easy range even then. So there's a huge difference between Mars and Earth's orbit, and Moon is kind of in between. Moon is actually closer to Earth's orbit, but you can see that Mars is probably doable, but Jupiter, no way. Jupiter is going to be a whole other line there. So if you're really taking a reasonable amount of stuff with you, like a rover or people or things like that, and you want to visit the planets, pretty much Mars and Venus are all you're going to get to with chemical rockets and people. And that's just kind of a fundamental fact of this ISP. Now, on the other hand, if you had one of these atomic rockets, then you can see you can get to the whole solar system. And in fact, if you read the papers of their plans for their atomic rockets, they were like, oh, let's go out and we'll swing by Ganymede on our way to Neptune. And, they actually had mission plans that made perfect sense. And it was actually kind of practical because they had such a huge spaceship, because it all scaled very well, that, they had no trouble bringing luggage. In fact, they had things like, a 2-ton barber chair on board their cruise ship as a plan. So they had they really had no weight limitations because there was so much power. So that was actually quite a plausible thing. I mean, I wouldn't want to, the reasons against it are more the environmental impact than the physics. There's plenty of radioactive fuel. There's plenty of, it's actually required less radiation in the atmosphere than people were already doing at the time, just because of the Cold War testing. So, and now probably these days, of course, you wouldn't start out in the atmosphere. You'd have the option of getting up to orbit with chemical rockets and then starting your atomics from then. But it is very plausible to tour around the, at least from a physics standpoint, very plausible. It may not be from a politics standpoint or a human preference standpoint, but to tour around the solar system if you're willing to go to atomics. But it just looks like it's not going to happen with chemicals. Then, if you really are thinking about going to the stars, you can see that way over there to the right, you just see that curve coming in. Basically, there's just nothing that gets you there that we have on our plate right now. We're just way outside of the range, even if we have ISPs in the order of 10,000. And there are ideas about how to improve the atomic system to build that. There are ideas about how to build ion engines that go up to about ISPs of 20,000. There's no fundamental technical limits in that say we can't do it. We just don't know how to do it. So right now, we fundamentally just don't know how to get to the stars. And that's, and now in that case, I'm doing a little different calculation. I'm not doing a delta V calculation. I'm doing a time calculation, because I'm assuming that we're not, that we have to go at least 1% of the speed of light, so that, it takes a lifetime to get to the nearest star, or a couple of lifetimes to get to the nearest star. So that's the other way that you can push this, is of course you could take longer. If you're willing to take 100 lifetimes, then maybe we are within shooting range. So that's where the links, I think fundamentally star travel is going to be a slow business. Unless we come up with some completely different idea other than rockets or ground-based lasers or even atomic rockets. Star travel will fundamentally be a multi-generational kind of a thing. And so it's a little bit discouraging news for the would-be star traveler. But it at least shows you, what's easy, what's possible, what's the space of what's the possibility space. And of course, somebody could invent something new, and maybe one of you will, that opens up the possibility space. So a lot of the things in this possibility space, weren't imagined 100 years ago. Actually, all of them were imagined 50 years ago. So it's interesting that the possibility space has not opened up much in the last 50 years. In fact, in certain sense, it's almost closed a little bit, because, in the 1960s, people really were seriously thinking about making these atomic rockets. So I'm going to stop there for questions about ISP limits, rocket equations. Does anybody, let me see if I can get back to my stop
Thanks,
sharing.
Danny. Yeah, great intro to all the complexities involved with navigating around the solar system and getting out to the stars. Anyone have any questions for Danny?
I might have a small one as I don't see anyone jumping. I was wondering if we found a way, I don't know much about atomic physics.
See, I'm not hearing you very well.
Sorry, is it better right now?
Yes, that's better.
Nice. I was saying I don't know much about atomic physics, but I was wondering if there was any way, probably that has been thought about, to make a kind of slowly triggering atomic explosion. That's not just one shot, but maybe a progressive explosion somehow.
Yeah, there have been, there was a very messy project to basically have an atomic reactor and use the reactor to heat up fuel that was shot out. And such a rocket was actually built on the ground. It never flew, but it made a huge radioactive mess, and that's still there actually in Nevada. And then there are possibilities of fusion. So if you could build a fusion system, and of course people are working on ways to do that on Earth, then you could in principle use that power from the fusion system to, for instance, drive a laser or an ion engine, or even shoot a plasma out one end. So I would say those are all conceptual possibilities, but nobody's actually engineered yet a practical rocket to do it. And in particular, I think the fusion one's interesting. If you could get magnetic confinement fusion to work in a bottle, then you could presumably let it out a little hole in the bottle, and you'd have a different kind of a rocket that, but nobody's ever designed one of those enough to even calculate the ISP. So yeah, that's a potential where a surprise might come.
And if we think the other side on the very slow approach, as there is no friction in space, could we imagine a system that just uses a bit of inertia from the planet centrifugal force, and then maybe a bit of, I assume everyone already had that idea before, but the solar powered magnetic steering. So for example, I've seen that some,
yeah, so that's a very good thing. And in fact, things that have gotten out of the solar system have used that technique. There is a way of kind of borrowing stealing some delta V from a planet. And because planets have so much mass, they don't notice the difference. And so there are sort of slingshot orbits and things like that use planetary. Of course, you can never get any velocity of that that's greater than the velocity that the planet is going around the sun. So for star travel, it's not terribly useful. For getting out of, for getting out of the gravity well of the solar system, it is useful. And so, right now that is our best technique, and it is the only way that we've gotten even small satellites sort of on their way out of the solar system. The original Voyager satellites are actually on their way. They're free of the solar system's escape velocity, and because they use those kind of slingshot orbits. So there's no known, but that doesn't get you going very fast. I mean, they've been going for decades and decades, and they're just reaching the edge of the solar system right now. Depending on how you define it, maybe just past it, but they've got a long way to go for the next star. I mean, I don't know the calculations, but I suspect it's many thousands of years. So I think the fusion thing that you said is probably more promising.
Thank you.
Danny, I don't know how long you wanted to talk on your 1,000-year clock project. So,
Well,
do
I
you
think
want to
that
switch to that?
unless somebody else has another question about the rocket equation, I think it's a very core thing you got to keep in mind in doing any space things. But yeah, let's say that you go the other direction. You say, well, okay, well, we'll go as fast as we can, but maybe it'll take us thousands of years. Can you really build things for thousands of years? And putting aside the question of whether you can do it in space, I'm actually thinking about building things that last for, machines that last for thousands of years in physical space. So I'm going to try to do the share again here. And see if this works.
We can see it.
Okay.
Although it's still on the rockets a little bit, yeah.
Still on rockets. Okay. Well, let's see. Yes. You know what? I think I can use my mouse if I don't go to play mode.
That's fine. It's still big enough, I think.
Yeah. Okay. So I did get interested in how much our time scale of what we sort of consider possible limits us. And I was really interested when I discovered that in New College, Oxford, they were replacing the oak beams with some beams that were from trees somebody had planted a few hundred years ago to replace the oak beams with. And that made me realize that we kind of define for ourselves how big our future is. And since I grew up in the 1960s, the future kind of stretched out to the year 2000. And then I found by the 1990s, the future still kind of stretched out to the year 2000. So it was as if this future had been shrinking by 1 year per year for my entire life. And in fact, in many ways, this future is much shorter than it was when I grew up as a kid. People really don't think 50 years out or 100 years out. And I think that's unfortunate. And I sort of felt a little cheated by that. So I decided I wanted to work on a project that lasted for much longer. So I started sort of fantasizing about this trail that led off into the mountains, and somewhere deep in the mountains was a clock buried inside of the mountain that would sit there ticking for literally 10,000 years, and that people might forget about it and rediscover it, and that I actually wanted to build such a clock. And so in my fantasy, you sort of knew it was out there, but you couldn't really see anything. And then you'd find this kind of a hole someplace, and you'd go deep in a mountain, and you'd find this spiral staircase with machinery inside of it. And you'd climb up to the machinery, and you'd go past all kinds of crazy mechanisms. And then when you reached it, you would end up finding a clock that read the date, not of the current date, but the date of the last time somebody was there. And it would be ticking. And when you wound it, it would wind forward to the current date. And you notice I have the date as a 5-digit date down there, because for 10,000 years, you have the Y10K problem to solve. And so you would basically wind it forward until it came to the current date, and it would show the sun and the moon and the stars or something like that to know that you had been there on that date. And so that started me thinking about, how do you actually build a machine that could last for 10,000 years? And of course, electronics can't last that long. The only thing that can last that long is simple mechanical things. And so I started building things. This was an early prototype, which is now in the London Science Museum. That has an astronomical display on it here. And it has a kind of digital computer counting the time. This is a prototype of a piece of it, which is already displayed, which is, if any of you are ever up in San Francisco, you can visit the Long Now Foundation, which is the foundation that was founded around this clock, and that's sitting there. You can see that piece of it and some other parts of it. That's basically an orrery that shows actually the positions of planets. It's a way that when you get to the clock, you can see that in fact it's keeping the current time, that the planets are in the right place. And then I started exploring around the Southwest for a long time. I had a very specific idea of what I was looking for in terms of mountains, and eventually did find an area of right near the Texas-New Mexico border of some very isolated mountains that had the right kind of geology. And in particular found this, which had a south-facing cliff in the right direction. And fortunately it was, I mean, I explored around various places. The first place we did manage to get was a private piece of property in the middle of a national park. But when we really went through the logistics of getting all our construction equipment through the national park, we realized that was not very practical. But this place was interesting. It was actually owned by a friend of mine, so who was Jeff Bezos. And so he actually volunteered the land and to help pay for the construction of the clock. And so of course we had to, do core samples, drill it, make sure, what was there underground and the limestone. And it was deliberately chosen to be out in the middle of nowhere. So we had to build a little city for constructing the clock. We had to build all the roads to it, everything like that. We bought in all kinds of toys for building things. This is one of my favorites, this giant Dremel tool. You can see a person down here to give you an idea of the scale. And then a lot of it was just the logistics of getting stuff in. So we marked an X of where that door should be. Brought in, you can sort of see, bringing in the equipment to drill it and blast it, and started building what was going to be a tunnel going on 40 feet. And I was going to build a big chamber there. I had originally wanted a cave, but of course, that was a little asking too much to find a cave. So you can see that's my node, make it look natural, and then the shaft turns. So we were going to sort of make our own cave. And then we started blasting in the mountain and building the entrance. And then sure enough, when we went in 40 feet, we found something, which we weren't sure what, and went down in there, and sure enough, exactly where I had drawn the cave, there was this amazing cave. So then people started joking about we were going to find the clock when we got to the right place. But so you go through this beautiful cave, which just wonderfully grew there. And then we started tunneling out from it to where we want to put the clock. We also drilled down from the top, a kind of an oil well kind of drill. And at some point, the tunnel that we dug in from the bottom met the drill thing that we drilled down from the top. And once we got there, we put this giant reamer onto it. So this went up through the hole to the top, and then pulled that thing spinning up. I got off of it first. Pulled it up through the rock and cut this beautiful 4-meter hole that went up hundreds of feet up into the till it reached the top. And then built this special robot that was designed with a diamond saw to climb up that hole and cut a staircase. So there's the robot climbing up, cutting. And as it went up, it cut this, it was numerically controlled to cut this beautiful staircase for 300 feet as it goes up the 500-foot shaft. And as we're doing that, we start building the mechanisms. That's one of the larger gears in the clock, all built out of titanium and high molybdenum stainless steel. All kinds of parts of various sizes, giant Geneva mechanisms. So this is of course, a decades-long project, which, of course, turned out to be harder than we thought on everything. For instance, all the bearings, you can't make bearings that last for 10,000 years by normal methods. So we had to use ceramic bearings for everything. We had to grind giant pieces of quartz for the lenses because it required a lens because it keeps itself synchronized when the sun goes overhead. The lens focuses down light on a box, which warms up, and the expansion causes the clock to know that it's noon and readjust the clock. Here it is, the chamber that we started opening up in the middle of the mountain to actually build the clock chamber. So then we started bringing the machinery in, which of course, installing something in a 500-foot hole in the middle of a desert is also a pretty significant task. And you can see the machinery, the scale of the machinery that we've been installing, which we're in the middle of right now. So a lot of this, I mean, everything you see here is obviously installed, and you walk up past the machinery around the spiral staircase as you go up the clock. And then up near the top is a calendar system. There's the weight that hangs down, that drives it. There are these beautiful giant bells that we made. That one of the things the clock does is that when you wind it up, when noon comes, it rings a sequence of bells, but every time it rings the bells, it has 10 bells and it rings the bells in a different order. And Brian Eno figured out that if you did that, you could ring a different sequence every day for 10,000 years. So one of the fun things about this project is I get people like him helping on it. So these are giant cast bells, which are also an interesting design. The clock itself has, is one of the most complicated pieces of mechanics that's ever been built. In some sense, maybe the most. It's hard to imagine. And then, but and maybe actually that's a good place to stop, I think. So we're actually doing it. It's slowed down a little bit in the last couple of years because of COVID, or the last year because of COVID. But we're getting very close to, having a working clock. So it's now down to years, not decades. So I know I've used up my time, I think. And I want to give a little bit, if people have questions. We've got maybe 10 more minutes. I'm going to leave a little bit of time for questions.
Thanks,
so it is
Ace,
possible.
so much.
Yeah, it is
that was
possible to
fascinating.
engineer. Yeah, it is possible to engineer things that last for 10,000 years. So space has another set of problems, but this makes me more optimistic about making 1,000-year starships.
Any questions for Danny on this?
I have some questions, but I want to leave the opportunity to other people because I speak too much.
One question about the location of the 10,000-year clock. It appears that the caves and the sort of borehole that you've drilled reveal or uncover sort of several thousand years of Earth's history, sort of recorded in stone.
Several million, actually. Yeah.
Several.
About 60 million years. And yeah.
Have you found, or are you considering ways to connect that sort of permanent record of history to the 10,000-year clock and what it represents?
It's a really good question. I mean, one of the things that became apparent to me as we sort of went through these layers of geology is just how short 10,000 years is
Yeah.
in sort of geological time frame. And I think that's been a recurring theme of the project, although 10,000 years is sort of an interesting time because it's the time of human civilization. It's kind of how long agriculture has been around. But yeah, when you start dealing with geological times, it really gives you a completely different perspective on things. And so, for instance, if you take an issue like global warming, the 10,000 year time frame, we actually had to worry about like, well, what happens if the solar ice caps melt, because that changes the rate of the day. And so the clock actually had to have mechanisms for adjusting the rate of the day, that as if the solar ice caps melt because of global warming. And that's partly what those lenses and things were for. But on the geological standpoint, we run through layers of way worse things happening to the Earth's ecology, and realizing that, okay, this is really a problem for human civilization, but it's not a problem for the Earth. The Earth's been through way worse than us. And in particular, probably the biggest chemical disaster of the Earth was the plants, which created oxygen, which rusted everything and completely chemically changed everything and made things unbearable for many forms of life. So it does give you a kind of different perspective of these different timescales and an appreciation of how short the human timescale really is. So we have looked for ways of connecting it, but they're so far apart still.
I have more of a comment than a question. I thought this was super interesting and just like a really, really beautiful idea. And it just when I first read the reading that was sent out too, the first thing I thought of was like Stonehenge or something. And like in 1,000 years, if this has been forgotten, stumbling upon it, and like, did humans really make this, or was it something else? Or I don't know. I just think it's a really beautiful concept. It makes me want to like write a story or something. Like, I don't know.
Well,
that's just comment
thank you.
on it.
Well, no, well, thank you so much. And that's really, I mean, that's the most interesting thing about it is, I mean, when you say write a story, in some sense, what it is a story. And the thing that has excited me most about it has inspired other stories. And so many stories now have allude to it or connect with it. Actually, Neil Stevenson wrote this book Anathem, in which it's about this alternative future in which people build 10,000 year clocks. That's a story, but people have written children's stories. And that to me is the most satisfying thing about it, because of course stories are really the longest lasting human things. But yeah, I think the connection in many ways, because I'm not a writer, I'm an engineer. This is the way that I've written a story. And I do want it to be a symbol in the same way we can look at Stonehenge, the pyramids, and sort of see that the symbol of our having a long past. We don't really have a symbol of a long future. And so we need something like that. So I hope this will become a kind of icon of that, even if it's just in people's imagination.
As an engineer, did you get a chance to build a miniature version of this magnificent long-term clock?
Well, we built pieces of it in miniature. And in fact, if you visit San Francisco, the best bar in San Francisco is the bar run by the Long Now Foundation, which has pieces. It's called the Interval. That's right. Yeah.
I went there 10 years ago. I remember now.
Yeah.
I saw it. Okay.
Yeah. And those are pieces.
That's what I was wondering. Okay.
Yeah, those are pieces of it. And so that's one of the lovely things about it too, is that the foundation, I think people need to think about the future. They need to believe in the future. And so the clock became kind of a lightning rod for people who had other ideas about the future and so on. So that became the Long Now Foundation. And there's a Long Now Foundation starting up also in Boston. If anybody's interested, I'm happy to put you in touch with them. But yes, that's the same place.
What kind of unit would you use to talk to another civilization in 10,000 years, a million years?
So,
How do
well,
they understand?
even talking to our civilization was a problem. So I didn't so much think about another civilization, but even how do you relate to somebody 10,000 years from now? And one of the things I realized that had been pretty constant for the last 10,000 years is that we have in common is that people did care about days and years and months. Probably didn't care about weeks, but days and years and months are all in fact connected to astronomical kinds of things. And so that's the reason the clock, the face of the clock actually shows days and years and months. And so you can connect to those. What the system we use for counting years is probably, will seem archaic, and, and it's designed so that people can add new ones and as they evolve. But the astronomical things, I think people will be able to relate to.
So there would be lunar months?
Yes, it shows, right. It shows the phase of the moon. It shows the position. It also shows the zodiacal cycle, which is a 25,000 year cycle. So it shows the position of the North Pole and the stars. So the North Star changes over 10,000 years. It'll be Vega in 10,000 years. So that's also displayed on the clock dial. If anybody's interested in the details, that you can look at the Long Now website, longnow.org. And I'll send that out in the chat or some.
Got you covered.
Thank you.
Danny, I'm sorry.
Go ahead.
Danny, I'm curious. So we're building at Space Exploration Initiative a sort of interplanetary timepiece, and it's still in development and concept. But I was wondering if you've thought at all about time cycles that aren't based on the Earth's cycles themselves, but the ones that exist in the rest of the solar system, or how to create clocks for that type of situation.
Yeah, well, I have thought of the sort of solar system as a clock. And that's an interesting one. And that orrery that I showed you was sort of experimenting with that. That's a very interesting one. The other interesting thing is that, of course, time is actually different outside of a gravitational field. And it's actually interesting, over 10,000 years, that is actually a noticeable difference. It's like a minute or something. So time actually floating out in space is different than time on Earth, just because of general relativistic effect. And over 10,000 years, it actually makes a difference, which really surprised me. I didn't realize that, that was sort of a human time difference skew would happen over 10,000 years. So, so certainly you'd think in terms of barocentric time. In fact, there's so many different kinds of time. There's a more technical paper if people are interested in it. There's a group of people that meet every year to decide whether to add a leap second. I call them the Time Lords, because they decide what time it is. But and actually, I'm always against it, although I don't get a vote. But I always talk to them and present that we shouldn't be adding these leap seconds willy-nilly. But and they, if there's a technical paper for them that kind of goes through the different kinds of time, including like barocentric time and so on. If you're interested, I'm happy to send it to it. But it's kind of amazing how complex a topic time really is when you really start looking at it in detail.
Truly, and yeah, absolutely interested in that paper. Thank you.
I was just wondering if you plan to, once the project is completed, do you plan to kind of cover it up and seal it, like a kind of time capsule, or leave it open to the public, or?
Yeah, it's intended to be open to the public. That was an agreement with Jeff when I said, okay, if we build on your land, you have to let people in to see it. And he agreed to that. So, and he's like, it doesn't really matter anyway, because I'm only gonna, me and my family will only own it for a few hundred years maximum. So it doesn't, I mean, that's just a little startup issue anyway. Over the long run, who knows what happens. But it is meant to be visited, but it's not meant to be easy to visit. So it's a commitment. You have to go out to the middle of Texas. You have to devote a full day to hiking into it. It's not an easy hike. So it's not going to be like a big high volume tourist place. It's going to be, but it is going to be some place where somebody who's very serious about it can go and visit it. Wind the clock and listen to the chimes and so on. Now, what happens over the long run is, I suspect, if it's like most human things, it will go through phases of being forgotten and neglected. But it's meant to keep on going even if people don't visit it. So it doesn't require humans to wind it. It actually keeps ticking just from the temperature difference between day and night. But it doesn't move forward until humans wind it. It doesn't show the new date until humans wind it.
But it knows.
It knows, right?
We are past 11. I don't know if you have something else after this, but we can go for a few more minutes.
Well, great questions. Maybe take one more question, if there is one.
Sasana's hand.
I do, but I also want to make sure if somebody else has one who hasn't asked a question.
Go ahead.
Okay. For 10,000 or other cycle clocks, are y'all thinking about perhaps incorporating life into one of these systems?
That's another.
Things like phylogenetic dating and other sort of methods of using DNA to track time. Is there a component for life in there?
I will have to send you. Okay, so we've thought about all kinds of clocks. Some of them are purely biological. One of the clocks I thought on early was almost a garden clock, that it had very slow growing things like bristlecone pine trees as the sort of slow ticks, and went to grasses and flowers and so on. And it was a garden that showed the year, or things that wore down and so on. So I've also written up some of those. So if you send me a note, I'll send some of the thoughts we've had about this. But I think it's a very rich area to be explored. So the answer, have we thought about it? Yes. Have we thought it through? No.
Fair
So
enough.
one of the nicest things about this is it's really kind of permission to think about things like this. And we've only scratched the surface of kind of explored one direction of it. But I could tell by your questions that you're thinking about some other directions, which I would encourage you to. I think it's a very rich area.
Thank you.
Maybe life is actually a clock that, or an organic kind of clock that another civilization left a few years ago, a few millenniums ago. Maybe we're just a clock.
Maybe we are.
Well, with that, I want to thank Danny for his time.
Always a pleasure. And yeah, please do follow up with me. I'm Danny@hillis.com is probably the easiest.
I'll put your contact in our class recap emails.
Okay, great. Alrighty. I'll look forward to hearing from some of you, and I promise I'd send you stuff. I'll follow up on that. All right. Thanks.
Awesome. Thanks again, Danny.
Bye-bye. Thanks for inviting me.
Yep. All right, everyone, we can start our 5-minute break here. We'll be back at 11:10. So, see you soon.